If you've ever felt that unexpected, sudden, sharp shock after sliding across a car seat, the one reaching for the middle door handle.
Oh, yeah.
Or maybe you've pulled off a woolen hat in winter and suddenly your hair just goes poof.
Right. Defying gravity, you've definitely experienced static electricity.
Exactly.
Yeah.
And it seems like just a tiny annoyance.
Okay. But that little spark, it operates on the exact same physics as, well, lightning, a massive, terrifying lightning strike.
Which is kind of mind-blowing when you think about it.
It really is. So today, we're doing a deep dive into the sources we've gathered that connect these two things from, the tiny electrons moving around up to a huge electrical storm packing millions of volts.
Okay. So our mission here is to get a quick handle on the basics, understand this whole charge imbalance idea, why it matters, and pull out some maybe surprising facts about safety and how lightning actually works. So let's start at the beginning. The atom.
Yeah, the absolute foundation. Everything's made of atoms. And you've got your three main parts: protons, neutrons, and electrons.
Right. Protons positive, neutrons neutral, electrons negative.
Exactly. And think of it like a mini solar system, the Bohr model analogy, right? The nucleus is the sun, holding the protons and neutrons together really tightly. And the electrons are like the planets orbiting around.
But the key player here, the one that causes all the trouble, is the electron, isn't it?
That's the one, because it's mobile. Protons and neutrons, they're pretty much locked in the nucleus. But those electrons, especially the outer ones, they can be knocked off, or an atom can grab extras, and that messes up the balance.
And that imbalance is static electricity.
Essentially, yeah. Static electricity is often called electricity at rest. The charge isn't flowing like in a wire, it's just built up, sitting there.
So what makes the electrons actually move from one thing to another? What gets them going?
Friction. Good old rubbing. When you rub two different materials together, the classic example is like a rubber rod and some fur, or maybe glass and silk. That rubbing action gives enough energy to force some electrons to jump ship.
Right. And it's only electrons moving, correct? The protons stay put.
Absolutely crucial point. Only electrons are gained or lost. So if an atom loses an electron,
it's got more protons left, so it becomes positively charged.
Bingo. And the object that gained that electron now has an extra negative charge, so it becomes negatively charged.
And no charge is created or destroyed in this process.
Nope, it's just rearranged, conserved. Think about walking across a carpet. Your shoes rub, right? The sources suggest your shoe soles often pick up electrons from the carpet, so you become negatively charged.
Ah, okay. And then I reach for the metal doorknob.
And ZAP. That doorknob is grounded. It offers a path for those extra electrons you collected to escape, to neutralize the imbalance. That's the spark you feel and sometimes see.
Gotcha. Now, why does this seem to happen way more in the winter? Is it just me?
No, it's definitely not just you. The environment plays a huge role. Static electricity loves dry air. Think wintertime heating or desert climates.
Yeah.
Humidity in the air, water vapor, it actually helps bleed off charge more easily. It provides a pathway. Dry air is more of an insulator, so the charge just builds up and up on the surface.
So that's why balloons stick to the wall better in winter, too.
Pretty much, yeah. Same principle. Your humidifier is actually fighting static.
Good to know. Okay, so now we have these charged objects, some positive, some negative. What makes them stick together or push apart?
It's a really fundamental rule of physics. Likes repel, opposites attract.
Simple enough.
Yeah. So two objects that both have a positive charge, they'll push away from each other. Same if they're both negative.
Repulsion.
Right. But if you have one positive object and one negative object, they'll pull towards each other. Attraction.
And this explains the crazy hair after taking off a hat.
Exactly. When you pull off that hat, friction happens. Electrons move, maybe from your hair to the hat. So now, every single strand of your hair might end up with the same positive charge.
And since they're all positive,
they all want to get as far away from each other as possible, so they push apart, and your hair stands on end. It's repulsion made visible.
Okay, so that's the small scale, hair standing up. But these forces, they scale up dramatically. Before we jump to lightning, you mentioned safety with even small sparks.
Absolutely. That tiny static discharge can be incredibly dangerous around flammable stuff. Gasoline fumes are the big one.
Right.
The sources are really clear on this. When you're filling a portable gas can, always touch something metal first, like the car body, away from the nozzle to discharge any static you built up getting out of the car.
And never fill the can while it's in the car trunk or the truck bed.
Never. Always place it on the ground. The ground connection helps dissipate any charge safely.
Okay.
And another thing, try not to get in and out of your car while the pump is running. Each time you slide across the seat, you risk building up another charge.
Ah, didn't think about that. That repeated motion.
Yeah, that little spark jumping from you to the nozzle near those fumes. That's how fires can start. It's rare, but devastating.
And it's not just fires. What about electronics? Computers and things.
Good point. Even a spark you can barely feel, or maybe one you don't feel at all, carries voltage. Our sources say a typical static spark can be like 3,000 volts.
3,000 volts. That sounds like a lot.
It is, voltage-wise. The current is tiny, so it usually doesn't hurt us much. But that voltage spike, it's easily enough to destroy sensitive electronic components, microchips, memory.
So that's why you should ground yourself before messing with computer insides.
Exactly. Touch the metal case of the computer, or use one of those anti-static wrist straps. It drains off any charge you're carrying before you touch anything delicate.
Okay, 3,000 volts for a spark. Now, lightning. What's the voltage there?
We're talking a whole different league. A bolt of lightning can measure up to 3 million volts, maybe even more.
3,000 versus 3 million.
Okay. It's the same fundamental process, static discharge, due to separated charges, just scaled up massively, enough to jump miles through the air.
So how does a cloud build up that kind of insane charge separation? It can't just be water droplets rubbing, can it?
Well, it's a bit more complex than just liquid water. It involves ice, actually, inside those big turbulent storm clouds.
Ice?
You've got strong updrafts and downdrafts tossing around tiny ice crystals and slightly larger slushy ice pellets called grapple. They collide constantly.
So it is still friction, but between different kinds of ice particles.
Pretty much. And there's a specific process, sometimes called induction charging or riming, that happens during these collisions. When the smaller, lighter ice crystals bump into the heavier, colder grapple, the lighter ice crystals tend to lose electrons, becoming positively charged. And because they're light, the updrafts carry them way up to the top of the cloud.
Okay, positive charge goes up.
And the heavier grapple pellets, which gain those electrons, become negatively charged. Gravity pulls them down towards the bottom of the cloud.
So you get this huge separation, positive top, negative bottom, like a giant battery in the sky.
Exactly. A colossal voltage difference builds up between the top and bottom, and also between the cloud base and the ground.
And when that difference gets big enough, boom.
Well, the spark can happen in a few ways. Sometimes it jumps inside the cloud, from the negative bottom to the positive top. That's in-cloud lightning.
Yeah.
Or it can jump between clouds, maybe from the negative bottom of one to the positive top of a neighbor. Cloud to cloud.
Right. But the dangerous one is cloud to ground.
That's the one. As that massive negative charge builds up at the cloud base, it repels negative charges on the ground below it and attracts positive charges.
So the ground beneath the storm cloud becomes positively charged.
Yes, and that positive charge tends to accumulate on taller, pointier things. Lone trees, buildings, radio towers.
Oh, okay. They become focal points.
Exactly. Now, air is normally a great insulator. It doesn't conduct electricity well. But when that voltage difference gets extreme,
it breaks down.
It breaks down. It's called dielectric breakdown. The negative charge from the clouds starts snaking down towards the ground in a series of steps. It's called a stepped leader. It's feeling out a path. And as it gets close, that positive charge on the ground, especially from those tall objects, sends up a streamer of positive charge to meet it.
Like reaching out.
Yeah. And when that downward leader connects with an upward streamer, bam! The circuit is complete. All that pent-up energy discharges in a massive flow of current. That's the bright flash we see as lightning.
Wow. Which explains perfectly why you should never shelter under a lone tree in a storm.
Absolutely not. You're basically standing right where that upward positive streamer is most likely to form, putting yourself directly in the path.
Makes sense. And the thunder that always follows.
That's the sound wave created by the lightning channel rapidly heating the air. It expands explosively.
Right.
And since light travels way, way faster than sound...
You see the flash first, then hear the rumble.
Then you can estimate the distance. Start counting seconds when you see the flash 1001, 1002, until you hear the thunder. Every second is roughly 1 mile the storm is away from now.
A useful tip. Now, people have tried to protect themselves from this for ages. Ben Franklin comes to life.
Yeah, old Ben Franklin. He didn't invent electricity, but he figured out lightning was electrical, and crucially, how to potentially control it, or at least redirect it.
The lightning rod.
The lightning rod. His idea was brilliant in its simplicity. Put a pointed metal rod high up on a building, higher than the roof line,
Okay.
And then this is key. Connect that rod with a thick metal wire or cable running all the way down the building and deep into the ground. It has to be grounded.
So what does that do?
It basically provides a much easier preferred path for the lightning strike. That positive streamer we talked about, it's much more likely to leap up from that pointed, grounded metal rod than from the building itself.
It intercepts the strike.
Exactly. And then that massive current, instead of blasting through the building, flows safely down the wire and harmlessly dissipates into the earth. Protects the structure.
Genius. But obviously don't try his kite experiment at home.
Oh God, no. The sources explicitly warn against that. Extremely dangerous. Franklin was lucky.
Right. But even with lightning rods, lightning is still incredibly dangerous.
Absolutely. Despite our understanding and protection methods, it still causes significant harm. The stats mentioned in our sources, around 100 deaths and over 500 injuries per year, just in the U.S. It demands respect.
It really does. So wrapping this up, whether we're talking about that little zap from a doorknob or that terrifying sky-splitting flash of lightning, the core physics is really the same, isn't it?
It is. It all boils down to the movement of electrons, usually kicked into motion by friction, creating an imbalance of charge.
And then nature's powerful tendency to want to snap back to equilibrium, to neutralize that charge difference.
Perfectly put. The drive for balance.
So here's a final thought for you, our listener, to chew on based on what we've discussed. We know static electricity is about transferring electrons. Some materials are good at giving up electrons like silk, remember? And others are really good at holding onto electrons like rubber or plastic.
Right, donors and acceptors, essentially.
So think about your everyday life. What common things around you, maybe things you wouldn't immediately think of, might be surprisingly good electron donors.
Or strong electron holders. Maybe your polyester shirt, the PVC pipes under your sink, even petting your cat or dog.
Exactly. Where might these hidden charge imbalances be building up all around you, just waiting for that tiny spark? Or maybe just subtly influencing how things cling or repel in ways you hadn't noticed before.
It's kind of fascinating when you start looking for it. That invisible dance of electrons really is shaping our world constantly.